Hello, in this video we'll show you how to use QGOpt library on the example of a 2-qubit gate decomposition. So let's start. First of all, please go to QGOpt documentation webpage and move to Quick Start subsection. Let's open the project in Google Colab. In the given short tutorial, we show the basic step on how to decompose an arbitrary 2-qubit unitary gate into a sequence of C0 gates and 1-qubit gates, as it is shown on the tensor diagram below. The decomposition can be found by minimizing Frobenius distance between a given 2-qubits unitary gate and its decomposition. For the beginning, let's import main libraries TensorFlow, Matplotlib, as well as QGOpt. So here, let's define an auxiliary function that returns Kronecker product between two matrices, A and B. A and B are square matrices with dimensions dim1 and dim2. The resulting matrix is also squared and has shapes dim1 times dim2, dim1 times dim2. And now we can move to the initialization of, first of all, circuit length, the amount of 1-qubit unitary gate layers. In our case, it's 4. Then let's also introduce C0 gate, 4 by 4 matrix. As all the unitary gates we work with are elements of Stiefel manifold, complex valued Stiefel manifold, let's initialize M, Stiefel manifold element. Our target U is a 2-qubit unitary gate. It has shapes 4 by 4 and can be generated using m.random shapes and type. After that, let's initialize all the 1-qubit unitary gates. Each of these gates has shapes 2 by 2, and total amount of this gate is 2 times circuit length. That's 2 times 4 equals 8. Now we have to introduce TensorFlow variable. And as TensorFlow optimizers are more stable with real values tensors, we convert complex valued tensors U into real valued tensors U here, using this command, QGOpt manifold complex to real. After all the initialization is done, we can move to the optimization loop. Here we minimize the Frobenius distance between the target 2-qubit gate and its decomposition. As usually during optimization procedures, let's set an amount of iterations. In our case, it's 500, and learning rate 0.2. For the optimization, we will use Riemannian optimizer. Here we pass M, that is an example of complex Stiefel manifold, to guide optimizer on how to perform an optimization on complex Stiefel manifold. So our optimizer here is QGOpt optimizers Riemannian atom. And let's also introduce an array that will later be filled with errors on each iteration. Then let's move to an optimization iterative procedure, as usual. It's worth noticing that on each iteration, we reconstruct the sequence of unitary 1-qubit gates and CNOT gates and compare it with what we have to obtain, that is 2-qubit unitary gate. First of all, let's convert back to complex our 1-qubit unitary gates using this command QGOpt manifold real to complex. Then let's create layers of the sequence. The first layer includes 2 1-qubit unitary gates. On the second layer, we add CNOT gate and again 2 unitary 1-qubit gates, and we repeat this 3 times. After the sequence is generated, we compare it with the target 2-qubit gate by a calculation of Frobenius distance between two tensors. Then we calculate gradients and ultimately find an optimal decomposition. Let's see what error can we get during this optimization procedure and plot errors. So you can see that in 500 iterations, the error or Frobenius distance between 2-qubit gate and its decomposition decreases from 1 to almost 10 to the 10th power, almost to 0. That is, our decomposition is quite accurate. So thank you for watching this video on QGOpt application to 2-qubit gate composition.